Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics. We have been discussing about the phenomenon of rectilinear propagation of light. What do you mean by rectilinear? Light travels in the form of straight line and casting shadows, and the contents of this lecture are formation of images, explanation using wave theory, area of half period zones, resultant intensity at any given point. Then we will have a short discussion on plane diffraction grating. What do you mean by rectilinear propagation of light? As I told you, when light is incident on an obstacle, here the obstacle is a person standing, a boy standing, and the wall is there and the shadow is cast. So, the formation of shadow which you see here can easily be explained if light is travelling in straight lines. So, the Newton's theory will be definitely much easier. Newton's theory is accepted, it will be easier to explain the shadow cast, because the light is travelling wherever the obstacle is there, boy is there, light will not be able to pass through the person and the image will be formed on the wall. The shadow cast can be explained. On the other hand, if you talk of diffraction, the light bends. Now, everybody will be asking, the light is bending, now why should the shadow be formed? Inside the shadow there should be light. Indeed, inside the shadow also there is light. Light undergoes diffraction, there is definitely bending of light beam is there. Light really bends when it is incident on a boy or a obstacle, but the intensity bending is there, but the intensity is produced because of the light beam that will be incident on the wall extremely small, so it appears to be dark. So, that is the essence of the thing. It is more of a mathematical approach, but the essential point is what I told you just now. A plane wave front, the light has come and it reached a place up to this ABCD up to XY, and wherein you have the light wave, the plane wave front of the light beam has been constructed, and in that construction we have the Fresnel zones. There are the Fresnel zones, first zone, second zone, so on, and we want to calculate the intensity at the point P. What is the point P? Point P may be here, right? You should understand it is somewhat difficult, right, but the point is I want to calculate intensity at this point P, and point P, because the bending there is some light, but the light intensity is so weak, that is what I am going to prove. The intensity, there is bending of light is there is light inside the shadow, but the intensity of the shadow, intensity produced by the, even though there is bending intensity, it is found inside the shadow, intensity of light is so small, so that it can be eliminated or is 0, and that is the reason why it appears to be dark. Okay. So, the off period zones, as I discussed, they are the off period zones, and I showed you the value of the distance between the m1 and p is p plus lambda by 2, and these values I am writing here. Okay. m1p is p plus b lambda by 2, m2p, that is the distance between the second zone and the point p, m2p is p plus b plus 2 lambda by 2, b plus 3 lambda by 2, etc. Okay, they are the distances, right. Okay. So, the area of the first half period zone will be given by pi times Ym1 square. Ym1 is the radius of the circle, right. So, pi r square, Ym1 square multiplied pi into r square. Ym1 is the radius, Ym1 square gives the area of the first half period zone. So, that is what I am writing here, pi into Ym1 square will be pi times m1p square minus op square, this is the Ym1. So, this is what I am showing here, and that will be equal to m1p square minus op square, but m1p is p plus lambda by 2 as I showed earlier. OP is the distance, right, between the source and the point where I want to calculate intensity, that is B, as I showed you earlier. So, this is the thing that you are having, pi into B lambda into plus lambda square by 4, that is what you will be getting now, cancelling these things. But you know, the second term can be omitted because it is so small, it can be omitted, and it ends up with the result as lambda is small, lambda square term can be neglected, and you end up with the statement the area of the first half period zone is pi b into lambda. It has been shown in red color because of simple reason, the area of each and every half period zone will be equal to one another. Area of the first half period zone is pi b lambda, second zone also will have the same area pi b lambda, third also will have the same area, third, fourth and so on. Okay, that is an important point. So, the area of the first half period zone is pi b into lambda. Okay. Then there is the first half period zone, the radius, the area of the first half period zone. Now I am talking about the radius of the first half period zone is Ym1, that is equal to square root of b into lambda. The radius of the second half period zone is Ym2, that will be m2p square. You can again refer back to the diagram I showed, minus op square to the power of half, that is p plus lambda to the power of 2 minus b square to the power of 1 by 2, that will be square root of 2b into lambda, the natural numbers. So, R1 is b into lambda to the power of half, Ym2 is 2b into lambda to the power of half. The area of the second half period zone will be the difference between the two, right. The second half period zone will be the difference in area between the total and the first half period zone. The area of the second half period zone will be Ym2 square minus Ym1 square multiplied by pi. So, that will be equal to again pi b into lambda. So, the area of the second half period zone is pi b into lambda, first half period zone is also pi b into lambda. So, what I am trying to tell you is the area of the first half period zone, second half period zone, third half period zone, all of them will be the same. Okay. The area of each half period zone is the same and it is equal to pi b into lambda. And again the intensity of the light coming from each and every thing will be m1 will be the intensity of light coming from first half period zone, m2 second, the m3 the third half period zone and so on, right. That it keeps on decreasing. The effects at a point P, our aim is to determine the intensity at the point P. Where is the point P? This is the point P, right. This is a point P, P may be a point here, light is coming here, and I want to find out the intensity of light because the light is bending. What is the intensity of light at that point P? Intensity is very high, then it will be bright. It is not bright, it is dark. You get the shadow that you all know how to explain the shadow form, that is using wave theory, that the bending is there, but the bending is there and the intensity of light caused at that point is so small. That is what we want to prove. You have the effects at the point P will depend upon the distance of P from the wavefront, the area of the zone, the obliquity factor. Obliquity means the angle of the elevation between the wave, the off period zone and the point. Hence, the area of each zone is the same, that is the important point. The secondary waves reaching the point P are continuously out of phase, that is the phase difference between each zone will be pi by 2, right, lambda by 2 or pi, and in phase with reference to the central or the first off period zone. Let m1, m2, m3 represent the amplitudes of vibrations of the ether particles. As I told you, Fresnel and Huygens were very much ahead of Rayleigh and others, who did away with the ether, or the present day understanding of light is light doesn't require any medium. Light is coming from the sun. Where is the medium? There is no medium to carry light. Light doesn't require any medium to travel. But according to the Huygens theory, they assume that a medium called ether, the particles are vibrating, and the secondary waves are produced and so on, the off period zones and so on. So, as we consider the zones outwards from O, the obliquity increases. So, from the first off period zone, the third or fifth, the obliquity factor will be the angle that is made by the off period zone with respect to point will keep on increasing. Okay. M1, M2 are continuously decreasing order. Thus, M1 is slightly greater than M2, M2 is slightly greater than M3 and so on. A phase difference of pi is there between any two consecutive zones. A phase difference of 2 pi corresponds to lambda, it corresponds to T. The difference in the phase between the first and second is pi. So, pi is what? T by 2. That is the reason why it is called half period zone. Hence, the displacements of the ether particles due to odd numbered zones is in the positive direction, due to the even numbered zones will be in the negative direction at the same instant. That is what I showed in the earlier picture also. M1, M2, M3, M1 is a positive, M2 is negative, M3 is positive, M4 is negative and so on. That is what we showed by means of arrows. Now, as the amplitudes of gradually decreasing magnitude because of the obliquity factor, the amplitude of vibration at P due to any zone can be approximately taken as the mean of the amplitudes of the two preceding and succeeding zones, two zones. So, M2 will be the amplitude of the first zone and the third zone divided by 2. So, M2 will be M1 plus M3 by 2. Okay. That is what you write the amplitude. The intensity is what? The square of the amplitude is called the intensity. The resultant amplitude at P at any instant is given by A is equal to the amplitude or the displacement caused by the light coming from the first off period zone, that is M1, the light coming from the second off period zone, that is M2, coming from third is M3. As I told you, they are alternately positive and negative because they are out of phase. Light coming from first zone, it differs from by a phase difference of pi from the light coming from the second zone. That is the reason why you have alternately positive and negative. They will be trying to annul each other. The constructive destructive interference, phase difference of 2 pi equal to 0, or a difference of phase difference pi means it will be positive and negative. That is the reason why you have M1 minus M2 plus M3 minus M4 and so on. Okay. So, A will be equal to M1 by 2, I can write A equal to M1 by 2 plus M1 by 2, I split up M1, right, M1 by 2, then I take this M1 by 2 here, minus M2 plus M3 by 2, then M3 by 2 minus M4, M5. Now, this M1 and M3, this the whole thing will be more or less equal. So, that is equal to M2, therefore, M2 will be M1 by 2 plus M3 by 2, and M4 will be equal to M3 by 2 plus M5 by 2. I am going to show that these terms will be getting cancelled, right. M2 is the average of M1 and M3, right. So, these terms can be cancelled, and so the resultant amplitude will be M1 by 2 only. So, A is equal to M1 by 2 plus M1 by 2 if you have got n zones, if n is odd, if n is even, the entire plane wave front is divided into n number of zones. If n is even, A will be equal to M1 by 2 plus M minus n minus 1 by 2 minus Mn if n is even. As the amplitudes are of gradually diminishing order, Mn and Mn minus 1 tend to be 0. So, the resultant displacement will be M1 by 2. These two expressions that you have got here, irrespective of the fact that n is odd, the plane wave front is divided into how many zones, whether it is odd or even number, the resultant will be depending on only M1 by 2. The resultant amplitude will be M1 by 2. Okay. The intensity, as I told you, is the square of the displacement. In physics, intensity is the square of the displacement everywhere. So, I will be equal to m1 square by 4, okay, that is m1 square by 4. That is the important point, right, that is the important result that you are getting. So, the essential point is, if the plane wave front is divided into 100 off period zones or 200 off period zones, whatever be the number, the resultant intensity that you are getting at the point P, where the boy is standing at the back of the boy, the intensity of light that is coming is due to only the light, the amplitude of the first off period zone. What is m1? The light coming from the first off period zone, that is your displacement cost is m1. The intensity will be proportional to m1 square by 4. It is 1/4 of the displacement square is the one that you are getting as the resultant intensity. It will be extremely small. What I am trying to tell is only the contribution to the effective light that will be reaching at the point P at the center of the image of the boy, or any obstacle at the center of any shadow that is caused, will be due to the light passing through the first off period zone only. But even if you place a small obstacle, that light will be cut off, cut the first off period zone. So, the resultant intensity will be almost 0. So, the intensity at P is only 1/4 of that due to the first off period zone alone. You forget about the second off period zone, third and so on, right. So, that is what I told you, whether you have 100 zones or 150 zones or 200 zones, it is immaterial. Only the light coming from first off period zone alone counts, because the intensity is m1 square by 4. Here only half of the area of the first off period zone is effective in producing the illumination at the point P. A small obstacle of the size of the half the area of the first off period zone placed at O will be 0, will lead to only 0 effect. While considering the rectilinear propagation of light, the size of the obstacle used is far greater, the obstacle generally of large area. So, all the off period zone will be cut off, including the first off period zone, which is the center. So, the resultant will be 0, hence the bending of light around the corners will be extremely small. So, what I would like to tell you finally is, when you have an obstacle in the path of the light beam, even if you treat light to be made up of waves, even if you assume that the light waves are bending, they really bend, that is diffraction. Diffraction is nothing but the bending of light waves. The light waves bend, but even after bending, the intensity that is caused or produced at the point P at any given point inside the shadow will be extremely small, and so it appears to be dark. There is no light inside the shadow, right, even though there is bending. That is how people were able to explain the formation of shadows. But the formation of shadows can be easily explained if you assume light to be traveling in the form of straight lines, as was done by Newton. But now the problem was, because light has a wave nature, because the bending is the one that leads to diffraction, the explanation that was given by Fresnel Huygens is definitely a remarkable one, and they showed that the intensity caused inside the shadow is extremely small. That is the reason why it appears to be dark. Hence, it looks as though light travels in straight lines, because the shadow is formed and the intensity inside the shadow is insignificant, it is very small. That is why you observe a shadow or darkness. I think this point should be made clear. I will go back to my old slides. Person standing, you get an image, but the point is, light really bends around the obstacle or the boy, but the intensity cost is so small, and it appears to be dark. We will now pass on to the case of a plane diffraction grating. What is a diffraction grating? You take a glass plate and you make the glass plate to become a grating. What is a grating? A grating is one in which you have rulings on spacings. A spacing is a slit through which light can pass. You just take a glass plate, you draw fine grooves, and you leave the intermediate spaces empty. The empty space is the slit. You have the Young's double slit experiment that we have seen with regard to interference. Similarly, there is opening here, there is opening, light cannot pass through this region, light cannot pass through this region. You take a small glass plate wherein light will pass through only the openings here, right. The openings will be very small, okay. There will be large number of openings within 1 centimeter. In a short while I will show how many openings will be there. In the openings very small, as I told you, light will bend. I told you that the hole should be very small. If diffraction effects were to be observed, or if the diffraction effects were to be profound, the size of the hole will be small. The size is so small, so light will undergo diffraction, and so we talk of plane diffraction grating. A grating consists of it's a device. It consists of very large number of narrow slits placed side by side. The slits are separated by opaque spaces. Opaque means light cannot pass through. Only the narrow regions through which light can be transmitted is called transmission grating. So this is the grating. In a glass plate that you do in the laboratory, a glass plate is given, several thousand lines are drawn, or several thousand lights openings are there through which light can be made to pass through. White light can be made to pass through, and you get all the colors, like the case of prism, you have the Webjior. Similarly here also makes a white light and make it to pass through the plane diffraction grating, you get all the colors. That is what you are observing now. Light is, this is called the grating element. A plus B is called the grating element, and you see here light coming here will undergo a bending, getting diffracted, and all of them, because you have got a lens here, all the light rays which are undergoing diffraction, they are bent, they will come to a focus at the point P1, right. Otherwise light wave would have gone to the point P, because the lens you got the bending is there, your lens is there to focus on the light rays which are being bent, and you get a focus at the point P1. Okay. The secondary waves from the positions of the slits interfere with one another, similar to the interference waves in Young's double slit experiment. Gratings are prepared by ruling equidistant parallel lines on a glass surface. Such surfaces act like transmission grating. That is, a transmission means light is allowed. XY is the grating surface, M1 is the screen. I showed you the diagram. M1 is the screen and XY is the grating element. The slits are parallel to one another. AB is slit and BC is an opaque portion. Each slit will have a width of A, and the opaque is B. A plus B is called the grating element. Let a plane wave front be incident on a grating surface. There the secondary waves are produced. The screen is placed at the focal plane. The point P where all the secondary waves reinforce one another corresponds to the maximum position of the central bright maximum. Now AB is A and BC equal to B. Path difference is so much, right. What is the path difference? The extra distance travelled by one of the light beams, right. This light beam travels through a longer distance compared to this one, right. Obviously this is the path difference. You know, we have the Young's double slit experiment, the path, extra path travel by one of the light rays per other, this is the extra path, right. Extra path AC, okay, AC travel by one of the light beams will be A plus B plus C, that is equal to A plus B, that is equal to AC sin theta, A plus B sin theta. A plus B is called the grating constant, right. A plus B is called the grating constant. For a grating with 15,000 lines per inch, the value of A plus B will be 2.54 by 15,000 centimeter. What is 15,000? 15,000 spacings will be there, or 15,000 opaque regions will be there in a grating. Okay. Such fine rulings and spacings, right. So with a diffraction grating, the wavelengths of spectral lines can be determined very accurately. The method involves accurate measurements of angle of diffraction. For white light using a spectrometer, by placing the grating on the prism table, the angles of diffraction of the different lines, the Webjior, the angle of diffraction can be measured. The angle of diffraction, so theta is the angle of diffraction, right. The angle of diffraction can be measured. You can have a formula A plus B will be equal to n lambda by sin theta, or A plus B into sin theta will be n lambda, and A plus B is called the grating constant. Okay, A plus B is the sum of the two things, that is the spacing and the ruling. You got a spacing through which light can pass, and there will be the spacing is a slit, and that is the opaque spacing, opaque region through which light cannot pass through. That is your B. A is the space through which light can pass. A plus B is called a grating constant that can be calculated within 2.54 centimeters. 15,000 rulings will be made, 15,000 spacings will be there. So, 15,000 rulings plus 15,000 spacings that is multiplied by A plus B, right, will be equal to 2.54 centimeter. The grating element will be 2.54 by 15,000. What is important is this equation is important. Sin theta is equal to n and lambda. What is n is 1 by A plus B, that is your n. You bring your A plus B to the right hand side. Sin theta will be capital N multiplied small n into lambda. What is small n? It is order number. So, unlike the prism, in the case of grating, light coming here, you get a series of lines in order of Vibgyor. You get a first order, then there will be again what you call a second order. The lines are getting repeated again. Depending upon your number of elements, you will have first order, second order, even the third order. How many rulings are made or how many spacings are made, first order, all the lines will be there. As I told you, by measuring this your theta for every line, your violet and green, everything, the theta will be different. Using the formula, the lambda can be calculated, and that is wavelength determination using a diffraction grating. Now, summary of the lecture will be as follows. The areas of each half period zone will be the same. The intensity of light found at any point due to the zones of a higher order are observed to be decreasing, even though the light beam bends around the obstacle. This is the important point. The intensity which is found inside the image is extremely small. A diffraction grating can be used to determine the wavelengths of spectral lines. The questions are, what are half period zones? What is the area of the first half period zone? Comment on the areas of the other half period zones. Next one, comment on the amplitude of light coming from the different half period zones. What is the equation which is used to determine the wavelengths of the different lines using the plane diffraction grating? With this, we come to the end of this lecture, and remaining things we will see in the lectures to come. Thank you.